Hello and welcome to Brenntag's technical webinars. Today we'd like to present to you successful jar testing. In the past we've presented a number of webinars that included many of the topics we have listed here: heavy metals removal, anti-scalants, oily waste, foam control, which was sponsored by the AWT, and coagulation flocculation. The coagulation flocculation webinar dealt with some of the topics that will lead into our talk today. We talked about definitions. We defined things like colloidal suspensions. We talked about the function of coagulation and flocculation. We also talked about coagulants and flocculants. We talked about product preparation. We touched briefly on jar testing. And then we also talked about plant applications and took questions. Today, I would like to introduce Ryan Kumpula. Ryan will be our presenter. Little background on Ryan. Ryan began his career in the chemical industry with a company called ChemPoint as an account executive. Ryan then joined Nalco Corporation as a technical sales specialist, where he further sharpened his water treatment skills. Eventually, he joined International Chemtex Corporation as a technical service representative. And then from there, he eventually came to Brenntag and is in our water additives group. Currently, Ryan is the industrial manager for water additives for our Pacific region. In his role, Ryan is responsible for leading the growth of our business, providing technical support to our diverse customers. Ryan resides in Phoenix, Arizona with his wife, Hana Lee, and their 4 children. It gives me great pleasure to introduce Ryan. And Ryan, take it away. The webinar is yours.
Hey, thanks, Kevin. I appreciate that. I thought I'd start today's webinar with a quote from Thomas Edison. He said that being busy does not always mean real work. The object of all work is production or accomplishment, and to either of these ends there must be forethought, system, planning, intelligence, and honest purpose, as well as perspiration. Seeming to do is not doing. The cornerstone of an effective liquid-solid separation treatment program is a well-run jar test. Understanding the need for strict testing protocol and a disciplined methodology will really mean the difference between a successful plant trial and potentially a disastrous scale-up. If you want to put it another way, a jar test can make or break the larger business opportunity. Therefore, it pays dividends to learn the right way to conduct a jar test. This webinar will help you to provide some specific tools, some templates, and practices to guide you to a successful jar test. As I mentioned, the goal of today's webinar is to help prepare you with some basic tools to conduct a successful jar test. In the hour or so that we have allotted for today's webinar, we will cover the wastewater application roadmap. We'll talk about the definition of a jar test. We'll discuss a successful jar test overview. We'll talk about the pre-work that you need to do in preparation for jar testing. We'll talk about plant applications. We've also got some videos that we'll show you to help really give you a better visual of what's going on with the jar test. And finally, we'll summarize what we've got. Every wastewater process follows the same principal steps to remove pollutants from the water. The first step is to create precipitation, which is the basic process in which a soluble substance becomes insoluble in solution. The next step that you see is coagulation, and that step neutralizes the particle charges to allow the smaller insoluble particles to gather together and they become larger. Flocculation further increases the size of the clump particles and increases the speed of separation. You can either achieve this by settling or raising those particles in solution depending upon the process that you're working with. And then finally, once the particles have been separated from the bulk water into a sludge, the dewatering step helps to reduce the volume of the sludge by removing water. A jar test is a small-scale simulation of the process in a water treatment plant to select and quantify a treatment program for removal of suspended solids or oil from a raw water or a dilute process or waste stream. The primary goal is to change the pollutants in the water to a form in which they can be easily separated. And you can do this by testing chemical dosages, you change up mix speeds, and settling times to set your parameters of the treatment program that are necessary to achieve whatever plant you're testing at their objectives to remove that pollutant. And then jars or beakers, as you see in this picture here, with different treatment programs or the same product at different dosages are run side by side, and then you compare those results with an untreated jar or one treated with the current program to come up with the final results. A successful jar test will basically follow the same steps every time. First, you want to replicate the system operation as closely as possible. Conducting site surveys, asking questions of plant staff will help you in determining normal plant operation. You'll then try to determine the best chemical program through jar testing. You'll test new products against the current program. You'll make adjustments from that when necessary further down the line. And then finally, after you've determined the optimal product choice, you should demonstrate your program to your customer. Highlight the benefits and capabilities of your solution, and then compare it with the current program in place. Thomas Edison was granted U.S. patent number 90,646 on June 1st, 1869. This was the first one of his 1,093 patents that he was granted over his lifetime, and you may not be familiar with this particular one. In the case of this patent, Edison heard about a problem he knew he could solve, and the problem was this. Whenever the Senate voted on an issue, each senator would stand one by one and call it his vote. When Edison saw this, he thought it was incredibly inefficient, and he thought he can come up with a way to simplify this process and skip that unnecessary and wasteful step of each senator standing up one by one to call it his vote. So Edison spent hours crafting his automatic vote-telling machine, and after patenting it, he brought it to the Senate. The chairman of the Senate committee was unimpressed with the speed in which the instrument could record the votes and basically told Edison that if there's any invention on earth that we don't want down here, that's it. Like many entrepreneurs or salespeople, Edison was sure he had observed a real market need, and he came up with a solution. He must have been extremely frustrated at his customers' inability to understand how he had saved them hours and hours by just changing their inefficient voting process. But the truth was Edison hadn't validated his assumption that the senators even wanted to change their system. In fact, as it turned out, that slow pace of roll call voting where each one would stand up one by one in Congress and other legislatures, that was an enabling process for them to filibuster legislation or convince others to change their votes. Edison's vote recorder was never used. However, rather than letting that failure destroy him, Edison recovered, and in the process he learned two important principles that led him to become a great innovator. I thought these were appropriate to our discussion today of jar testing. So first, he learned the crucial need to understand your customers, specifically the job they're trying to get done and why. And second, he learned the value of rapid iteration to get to the solution that his customers needed. You'll find that rapid iteration in jar testing will be invaluable in your work. And as Edison said after working through thousands of iterations in developing a commercially viable light bulb, I have not failed. I've just found 10,000 ways that won't work. Gaining customer commitment is key to a successful jar test. It's important to get buy-in from the customer before starting the jar test process to ensure that your efforts will lead to action by your customer. Getting agreement in writing ensures they are as committed to the process as you are, and also allows you to define parameters for a successful jar test. This step allows you to discuss any potential obstacles and plant conditions before starting, and hopefully eliminates any surprises down the road. This is also the right time to understand what a successful jar test will entail. Do you need to meet certain performance criteria? Will just meeting the existing program's performance metrics allow for a plant trial? Are there other economic considerations that must be met first? Also, understanding the operational conditions of the plant itself allows you to properly schedule your jar test, whether you're doing it on-site or if you're going to grab samples and do it off-site. Oftentimes, you'll find that additional jar testing is required to replicate a change in plant conditions that may affect your product dosing and choice. And if your jar test proves successful, you will also have created a roadmap for moving forward with the plant trial or having your products added to the plant's approved product list. As Peter Drucker said, there's nothing so useless as doing efficiently that which should not be done at all. If you gain commitment from your customer before you start, you'll avoid the fate of Thomas Edison and his automatic vote-telling machine and hopefully get some results. Understanding your customer's goals is key to planning your jar test. There are many factors to consider, and you should discuss with your customer to find these out before beginning your jar test. I found that using a written checklist or a survey form like I've got pictured here is helpful, as it helps guide me through the discovery process. And it also helps when putting together my written game plan later on that I can use to gain commitment. So I've got this stuff in front of me, and I can use it when I'm writing that report and moving forward. There are a wide variety of different types of applications where jar testing for a coagulant may be encountered. Here's a list of several that you may encounter. And as you can see, there's a wide variety of different applications, and as you can imagine, there's a wide variety of different products that you can choose depending on what you're looking for. The applications where flocculants are used can also vary widely by industry. Some examples you can see here are for sludge thickening and dewatering, dissolved air flotation units, clarifier solid setting, pond and lagoon applications, and many others. In the case of a dissolved air flotation unit, you might find that the polymers help entrap air in the floc, which enables it to rise faster. And then that entrapped air also helps the sludge dry faster as it gets to the top, so it performs a variety of goals there as it moves on. The next step is looking at the plant itself. What are the plant's operating conditions? Taking some time to walk around the plant and learn about the process flow and plant conditions will help you. And having a good understanding of the plant's operating conditions is critical, as there are multiple factors that could impact the jar test that should be considered. Some of these might be mixing times, retention times, flow rates. You might want to get a good idea of the plant history and the types of equipment they use, because all of those things play into planning your jar test and the outcomes. Find out if the plant is continuous flow or if it's a batch process flow, and if they also have regularly scheduled maintenance and performance reviews of the associated equipment and the feed rates. So is somebody on site checking the feed rate, checking the floc? Do they have some type of history, or do they have a plan in place? Because that will all come into play with the outcome of your jar test and also plant success. And remember to keep safety in mind. Note chemical storage locations, look for eye washes and containment. Those things will be important too, because you want to make sure your chemical that you choose can be safely applied to that plant. I've always found it extremely helpful in my understanding of a system to draw a simple plant diagram. It helps me to provide an overview of the plant and the process flow. And this can also be used as part of your written agreement and proposal to indicate chemical feed rates and locations, document mixing and retention times, and to indicate important water quality parameters as they change in the plant. You'll also find that many times plants don't have anything like this, and when you put that together, that's another valuable resource that you can provide for them. The next important step is to find out what pollutant or contaminant they are removing from the water. This is really the crux of the chemical program. By finding out what contaminants are in the water, you can tailor the chemicals you bring in your test kit. This will also help you in providing starting points for the type of coagulants and the flocculants that you use when you conduct your initial jar tests. Unusual contaminants or unique problems may require you to bring additional products that aren't part of your typical test kit. And an example might be if you're looking at a particular plant, so for a textile plant where they might be using one chemical to test, but when you do your plant overview, you notice that that's not quite working well, or they've got some operational issues that may be affected by a different product choice. So if you take a look at different products beforehand, you know to bring those with you, and you're better prepared when you actually get on site and do your tests. Spending some time organizing your jar test equipment beforehand will also help save you time in the field. I think it goes without saying that the more organized you are, the better off you'll be, and then you'll have less chance for being successful in the field if you've got everything put together. If you put together a sample kit of commonly used polymers and coagulants and you organize them by color and charge, that's always been a good practice, as it keeps things close at hand and it's really consistent, and it really saves you time in the long run. We talked about iteration before with Thomas Edison, and this is one area where you can really help yourself succeed by putting things in place and having a successful process flow. And if you take the time beforehand to think through what your goals are, that will also help you determine what equipment is necessary to bring with you in the field. As you can imagine, there's a wide variety of equipment that you can bring. Remember to bring your own personal protective equipment with you. Many plants will have gloves, eyewear, and earplugs, but it's best to come prepared with your own to ensure you're able to conduct your test safely and not have to go back and get something before you conduct a test. In addition to the specific jar test equipment, remember to bring a laptop or a notebook in which you can record your results. When you plan your test, you can put together an outline of what you'll test for and set up your worksheet ahead of time too. That'll save you some time in the field. Equally important in your equipment list is the appropriate equipment for preparing your product on site. If you are working with powders, including a gram scale, a beaker, and a magnetic stirrer are essential. With emulsions, a small hand blender will come in handy. When using liquid polymers, the use of dilution bottles and micropipettes will allow for ease of use and precise dosing of your polymer. If anyone has ever done any painting projects around the house, then you know that most of the work is done before your brush ever gets dipped into the paint can. The prep work makes all the difference in how smoothly your jar test goes, and making down your powdered products the night before is important. Emulsions can take between 30 and 45 minutes of setting time, so getting started on these right away will allow you to set up the rest of your equipment while you're waiting for those to set. Remember, dilute your products to the correct dilution strength to ensure that your calculations are accurate and your dosage rates can be replicated when you finally go up to plant scale. When diluting dry products, adding 1 gram of powder to 1,000 milliliters of water will result in a 0.1% solution. Powdered polymers require longer mixing and accurate weighing out for making up a stock solution. First, accurately measure out the powdered polymer. Have your water measured out in a beaker, mixing on high with a good stir bar. Using warm water will help to dissolve the powder. When you have the mixer on high, sprinkle the powder over the top and make sure it goes in grain by grain into the vortex for the best makeup. A clump will take longer to dissolve, and as you add the powder, it will swell up and have the appearance of a tapioca. Sometimes you call this the fisheye stage. The powder will pass through this stage and dissolve completely. It should take about 30 minutes to completely dissolve. And when the powder is completely dissolved, put it into a bottle and label it with the product name and dilution factor. It's also a good idea to put the date on the bottle, as cationic polymers only hold a charge for a couple of days and anionics may go on for a little bit longer, but putting that date on there will help you as well. Liquid emulsion polymers are easily prepared by dilution with water. We generally make up liquid polymers at a 0.1% stock solution. So you start by shaking the bottle of concentrated or neat polymer to ensure it's well mixed with the carrier. After you shake it, use a graduated 1 ml syringe and up-plunge the polymer to be used. Make sure you read the graduations, as you'll be adding very little to the water. And then once you've pulled the material up into the syringe, you might want to wipe the tip off so you don't include that extra material outside of the syringe in your calculations. Be careful not to shear the polymer. About 10 seconds of mix time with the handheld mixer, as you see pictured here, will help uncoil the polymer chain, but won't cause any shear. But that time is important to record. To make down a 0.1% solution, you first add 1 milliliter of neat polymer to 99 mils of water. This will make a 1% solution. Then you take 10 mils of this 1% solution and add to 90 mils of water. This will make a 0.1% solution. When we make a polymer down, we're inverting it and letting it unfold like a long strand of microscopic flypaper that will eventually grab hold of all the insoluble particles in the water that we're trying to remove. So you want to start the hand blender mixing in the beaker of water and get it ready for the polymer addition. While the water is being mixed on high, I'll play this again, plunge the liquid polymer into the vortex generated by the mixing water. This diluted polymer has to age for about 30 minutes to allow for maximum effectiveness. And when it's finally done, the diluted polymer should look like a thick, milky solution. So when we make a polymer down, we're inverting it and letting it unfold, like I mentioned, a long strand of microscopic flypaper, and you'll see that happen. I also mentioned the 10 seconds of time that you want to check here. 10 seconds will make a homogeneous solution will help avoid any polymer shear. High shear can deteriorate the polymer chain, so it's good practice to avoid the use of high-speed mixers, disintegrators, or centrifugal pumps in your plant. One thing to note here when you're discussing shear, you may have an actual shearing of the polymer chain itself during makedown, but you also need to be aware of flock shear, which may occur after flock is already formed when using a high-speed mixer, and that refers to shearing of the flock itself. Commonly used organic and inorganic polymers are listed here on this slide, and you may also find blends that contain a combination of both to achieve results that are better than when you just use each product individually. Organic polymers typically don't need to be made down before using, but the products can be diluted for ease of feed and dispersion during your jar test. Inorganic polymers must be fed neat, and using a microliter syringe is recommended for dosing. Blends are used just like the organic polymers. In addition to effectiveness in treating the wastewater, the cost, the availability, the pH, and sludge generation are all factors to consider when you choose a coagulant. Now that we've discussed the pre-work, let's get started in actually doing some jar tests. The first step in starting the jar test is obtaining a representative sample of the water to be treated. Are you going to jar test on site, or are you taking a sample and testing it elsewhere? You want to try to determine the amount of sample you need by anticipating the total number of tests you'll conduct and the size of the individual jars. Make sure you allow for sufficient volume to complete the verification tests such as pH, turbidity, metals, and others that you'd be looking at. The sample should be representative of system conditions, be well mixed, and have no chemical treatment in it. Once you have a well mixed and appropriate sample, you want to pour the same amount into each beaker. Remember, clean the beakers and the test equipment in between each test to avoid contamination from one test to another. You want to check the stir paddles and wipe them clean. You want to take any polymer that might have gotten stuck on there, might have got in there during testing off before you begin the next test. When you begin jar testing, you want to start by testing the coagulant first. Test each coagulant chemistry and run them side by side. Then you want to refine your dosages and then finally replicate the system operation to ensure that your jar test mimics the actual operations as closely as possible. Check your pH and remember to iterate the process by jar testing more than once to ensure that you can duplicate your test results. Number your jars left to right 1, 2, 3, 4. It's also good practice to use the product in order from the sequentially lowest numbered product from the left to the right. Example, in this picture we've got jar 1, then 2, 3, 4, and then you've got product TDJ5, TD24, JCU47, MI955, lowest to highest, left to right. Just staying in that order will help you stay organized in your jar tests as you run multiple jar tests. To begin, start the paddles mixing and add coagulant to each jar that you're testing to find an appropriate starting point. Oftentimes it's good to start with a fairly large dose just to ballpark your treatment ranges and to find out which products will have an effect before starting to narrow down those products. The faster you can iterate your process, the faster you'll be able to dial in your effective doses with the appropriate product. As the coagulants mix, you look at the pin flock to determine the best product. Usually vigorous mixing enhances the coagulation. You may need to look very closely and allow the system contact time to elapse before making a judgment call. Time your jar test and turn the mixer on and off periodically to observe what's happening. You might even start to see some separation at this point in the process. If you look at that jar, you see a little bit happening at the bottom. In this jar test, 4 different products and chemistries were added. Here it's important to duplicate the mixing time, system agitation, and start observing the pin flock to determine which one's your best performer. With time and experience, and as you do more jar tests, you'll find ways to speed up this process, but this is really where careful observation and consistent notes will come in handy. As you can see here, you can slowly start to see separation in some of these jars, but again, careful notes will help you as you conduct multiple jar tests with multiple products. And as I mentioned, keeping concise and consistent notes is critical to record your efforts. You want to notate the products used, you want to put the dosage and rating after each test. It's good practice to maintain the same order in your worksheet as you have with the jars themselves. Here we're dosing each jar with the same amount of each coagulant. Remember, keep track of which products don't work is just as important as which ones do. Elimination by just looking at which ones don't work is a great way to get towards something that does. As the jars continue to mix, you will hopefully start to see more separation of the flock. Here you can see that in jar 2 there's much better separation and clarity of the raw water than the others, and you can start to see that here at the bottom. You can start to see some separation there. One thing, I'll go back, one thing I've noticed too is as you look here, the light may not be good enough. Keeping a pen light handy or a flashlight with your equipment will help you. You could shine that behind the jars and really start to see separation too. That helps when you're looking for some separation there. Again, rate the performance of each product in your worksheet before moving forward. Remember, coagulation must occur before testing the flocculant. After you've determined the best coagulant, treat all the jars with the best coagulant and then test them with both an anionic and a cationic flocculant. You might want to start with 30% anionic and a 20% cationic and see which product combination provides the best results. Once you've determined whether an anionic or cationic charge is best, then you'll start to determine the best product by bracketing those original products with higher and lower charge flocculants. You can also test various molecular weights of the flocculant within the best charge density. In the flocculation step, you'll want to observe overall flock size, cell or rise rates, the overall clarity of the bulk water, and see if there's any remaining pin flock in the water. Here in this video, we're adding the same polymer to every jar at different dosages to compare the flock formation and clarity, and we're trying to refine our dosages here. You may want to vary the agitation of the jars to mimic actual plant conditions. Be careful though in setting mixing speeds, as too much agitation can cause the flock itself to shear, as I mentioned earlier. The time of polymer addition, the total mixing time, and separation time are critical and should be observed and notated. You can either prepare each dose prior to adding which can let you put them all in jars at pretty much the same time, or you can prepare each dose separately as we are here and add to each jar independently. Remember to note the dosage of each polymer though as you add it to the jars. And again, just looking at these different jars, you can start to see jar 2 is really starting to separate quite nicely compared to the others. Again, you can see we've notated that with each flocculant, one part per million was added. Keeping clear and consistent notes will help you when you summarize your findings and create your report, and will also help you if you need to replicate your jar test at a later date. Rapid flocculation mixing is conducted to help fully distribute the flocculant in the water sample. You should attempt to mimic plant conditions with both the speed and the time of the mixing. This is usually done at a slower mixing speed than with coagulation though, because you want to avoid product shear. Here you're looking for particle size to increase and for separation and clarity in that bulk water. With slow flocculant mixing, you are at a slower mixing speed than with the initial flocculation, and again, you want to try to mimic the plant conditions. Continue to observe the particles as they should begin to increase in size as they start to mix. The bulk water should become more clear, and with proper dosing, you shouldn't see any remaining pin flock. Careful of overtreatment though, because that might possibly reverse the separation. You might start to see the flock stringing together, you might see foaming and a reduction in overall clarity. The result should be a well-formed flock and rapid separation from the bulk water. Here again you can look at all 4 jars, and it's pretty obvious that jar 2 has much better separation and clarity. And again, look at that flock size, it's much thicker and larger than the other ones. So just on initial observations here, jar 2 again seems to be the clear winner. And this is just a picture to further emphasize that difference. Record your observations and results on your worksheet, and remember to indicate the flock formation and the clarity relative to the other products tested. The comment section allows you to make overall statements about each combination to help you choose the best program. Oftentimes you might have 2 products that are fairly similar in performance, and a final judgment may be made based on other factors such as economics or availability of the actual product. A few final points to consider as we come to the end of this webinar. Before we begin any work jar testing, you remember you don't want your jar test to suffer the fate of Thomas Edison's vote telling machine. Remember to get customer buy-in and commitment from the very beginning of the process. Having an agreement in writing with a clearly defined game plan will help to ensure that your efforts are rewarded. Taking the time to conduct a plant survey and understanding the system and problems they are trying to solve before you begin will help guide your efforts and streamline the process. We discussed the type of equipment needed and also the importance of understanding basic jar testing procedures. Remember to test all possible situations and record your data and observations to make sure that you can make clear and effective recommendations. Finally, once you've successfully completed your jar testing, you want to schedule a plant trial to prove your results in the field. We will discuss plant trials during our next webinar, which will take place during the first quarter of 2017. Stay tuned for details on that one, and we'll keep you informed. The best way to learn and improve your skills, remember, is by doing it yourself and conducting your own jar tests. I'll close this with a quote from Benjamin Franklin, which says, "Tell me and I forget, teach me and I remember, involve me and I learn." Thank you.
Ryan, thank you very much. It was an excellent job. If there's any additional information needed, the email addresses are listed for myself, Kevin Cope, and Ryan Kumpula on the bottom. We very much appreciate your time today, and thank you very much.